Hi everyone, welcome back to the channel. So the internet is absolutely ablaze with this new potential discovery of a room temperature ambient pressure superconductor reported by one South Korean group, but there's two papers that were released on the archive in July 22. Since then, basically, there's been a huge number of news reports going on about how this thing could be a novel superconductor, the consequences in terms of the new technologies. Things like superconducting stocks in Korea have been going through the roof. In the New York Times, there's been a new report this morning about how LK-99 is the new ambient superconductor of the summer. And of course, on Twitter, there's been like all kinds of people weighing in about whether this is a new superconductor or not. There's even been a Twitch channel which has been live streaming their experiment in replicating this new LK-99, synthesizing it and then seeing whether there's superconductivity or not. Of course, there's been all kinds of weird memes and things like that with fake reports of people verifying LK-99. This one is a supposed verification with basically a coin and a piece of fishing line. Memes about how this is the new ChatGPT, people anxiously waiting for new results on verifications, and of course now everybody is an absolute superconductor expert, right? This, in the scientific community, has been met with quite a lot of skepticism. So this is a very early tweet that Sankar Das Sama made just about 2 or 3 days after the initial papers were put on the archive. And already at this point, people were skeptical. If I just read out the tweet, he basically says that here's another claim of room temperature superconductivity and levitation by another relatively unknown group with limited background in superconductivity. In fact, they make 2 bold claims in one evening. Obviously, this is unlikely, but the boldness is breathtaking. I really like the way that he phrases this. Given this kind of backdrop, what I want to do today in this video is just to give you a little bit of a sense of why the scientific community is skeptical about it, and basically let's see whether we really have any hope that this will be really the breakthrough that it promises to be. Okay, the thing about this paper is that apart from the weird sort of writing, there's all kinds of peripheral things which raises a few red flags even before you really start to delve into the paper, right? If you look at the lead researchers in the paper, they come from this place called Qcentre in Korea, but actually if you go to the website, you can't actually get there anymore. I don't know, it's been shut down. It's a bit mysterious in itself. Oh yeah, it could be hacked with the intense pressure that people get. Yeah, it could be anything, right? But so about a week ago, there was another video by Dave Jones from EEVblog. I don't know, you guys might be familiar with it. At this point, when he made this video, this website was still up, right? And what you can gather from this website is that it's some kind of startup or some kind of commercial company rather than a research institution or a university. And basically what Dave does in this particular video is to debunk a particular demonstration of this material, which I think that this company is basically trying to sell. You know, this is basically their product. And the video involves basically a piece of this material hanging from some fishing line, and then they get a different magnet, and then they oscillate this magnet near this piece of it. When I saw this video for the first time, I also thought it's a bit weird. I didn't really know what to make of it, actually. Is this supposed to show superconductivity or something?
Maybe levitation.
Yeah, it's definitely
to mimic,
yeah, it's not really levitating, is it? It's like
it's in a string, so
yeah, exactly. But basically what Dave does in his video is that he basically replicates the same kind of experiment with a piece of copper, and then this silver thing here is some magnet. It's a weird shape, but it's basically just a magnet. And he can do the same thing, and he just says this is just Lenz's law, like you learn in high school, right? He debunks that part. Well, it's a bit mysterious what that demonstration was supposed to show, but anyway, the website's taken down regardless. Another weird kind of thing, which people have already talked about a bit, is that apparently the reason why there's these 2 papers is that this last author on the 3 author paper actually submitted it without the permission of the other 2 authors. That's also another very weird circumstance, which normally does not happen. And presumably they knew about this because these two papers appeared on the archive kind of at the same time, right? So they probably knew that this guy was going to submit or something, and then they made sure that they also had their version up on the archive, like on the same day. So weird circumstances. Another weird thing is that they've had this material since 1999. This is what the 99 stands for in the name of the material. They've had 20 years to basically perfect this material and investigate it. And I'm sure it's not, they just turned around this year and then figured out that it's, a superconductor. They've been playing around with this for probably decades. And considering this thing is a fairly easily manufactured material, and people are just like doing this in real time on Twitch, manufacturing this stuff and actually measuring its properties, it's a bit weird that all this is coming out right now. Another reason why people are very skeptical about this is that there's been lots of room temperature superconductivity claims in the past. And one particularly notorious case was this case by Ranga Diaz back in 2020. He, along with his team, claimed that there was a material that possessed room temperature superconductivity. Obviously, this paper, as you can see here, has been retracted now. This came to be retracted because this guy Hirsch, as famous from the Hirsch index, the same guy, he actually went after this group to show that basically there's something wrong with their results. And in the end, basically, they were forced to retract their results. But what's interesting is that even in this retracted paper, their claims are not even as profound as basically what's being claimed right now with this LK-99, right? So if you look at the claims there, it's temperatures of around 15 degrees Celsius, that's slightly like a cold room, and 267 gigapascals, that's 10,000 times the pressure of ambient pressure, right? Even these, what we now believe to be faked results, are actually quite modest compared to the results that are being claimed right now. Now, that doesn't really mean anything really, but this really would be such a massive advance in comparison to what's available out there at the moment. So that's basically some kind of peripheral information that you want to have in your mind. Just incidentally, this DS guy also published another paper just earlier this year, also of room temperature superconductivity, again at very high pressures, right? So this was accepted into Nature, presumably people looking at this also with quite an eye of skepticism. But what's interesting, even to look at the results from this retracted article, is that there's some key signals of superconductivity. If you're going to claim room temperature superconductivity, then there are some sort of key things that you probably need in order to get it through to Nature. And one of the key things is, of course, measuring zero resistance. And even in this retracted article, there is like this kind of plot here on the left where you see the resistance on the vertical axis and the temperature on the horizontal axis. And basically at some temperature, it collapses to zero. This is the classic hallmark of superconductivity. This is what Onnes saw back in 1911 with mercury. And this is still basically the classic signal that you really want to see. If you look at the results of the paper, it's just weird. There is a plot like this. This is in the 6th author paper. So there's a plot of the resistivity against the temperature. And indeed, there is this drop that happens at 110 degrees Celsius, not Kelvin, but Celsius. So this is like above boiling point of water. But it doesn't really drop to zero, right? And it drops to some value, which is, it looks like about 0.2 times 10 to the minus 2 ohms centimeters. And so if you compare this to the resistivity of, say, copper, this is like way higher, right? It's way higher. Its resistivity of copper is 10 to the minus 6 in the same units, right? So this is like 10 to the minus 3 versus this is 10 to the minus 6. If you just look at that, you'd say, yeah, it's not really. Of course, this later on goes down to smaller values. But the scale is so big, you can't really see what value this is really going to. It's looking at something on a huge scale when you really want to see the small values, right? That's a weird aspect of this. Really can't make heads or tails about it. From the 3 author paper, they don't have this classic resistance versus temperature plot or resistivity, but they do have the one graph that they do show about the resistivity is this one, where basically they show essentially at one particular temperature, I presume, of the voltage versus the current. And then so from that, you can work out the resistance. And apparently from this larger plot, they work out the smaller plot. And I assume they do something like this, and this is just my naive first year physics kind of method here. But if you work out basically the resistance of this, because V equals IR, right? So resistance is V divided by R. Okay, so you, for example, take one of these points here. Let's say it's about 0.1 microvolts, let's say, roughly. And this is 25 milliamps, okay? And so that will give you a resistance of about 10 to the minus 6 ohms, okay? And now to convert this into resistivity, we need to multiply by the dimensional factor, like how big this sample is. Now, again, they don't really tell you exactly the sample size in that paper, but in the 6th author paper they do, taking the sample to be this dimension and then calculating this A over L, you get a resistivity of something like 10 to the minus 7 ohms centimeters. Okay, now that is not really the same value that you get in this graph, right? That you're getting something like 10 to the minus more 10, right? So there's 3 orders of magnitude missing. Unless I've done something stupid here, you can tell me in the comments if this is all wrong. But I'm not sure even how they can get these values of the resistivity. Okay. Obviously, people have been trying to replicate these results, and so far, as for the resistance estimate, I think this is the closest that people have come. This is a very quick results coming from Southeast University that came out on the 2nd of August, and they basically managed to measure a zero resistance, but they could not do it at room temperature. They need to go down to something like 110 Kelvin in order to see the resistance dropping to zero. So basically the graph on the left here is the results, and at some temperature around 110, the resistance basically goes to somewhere in the noise, right? But even this has been criticized quite a lot because this graph doesn't really have the classic shape of superconductivity, what you'd expect. So if you replot that same graph on a linear scale, then it has this kind of more like curved dependence, not like this sudden drop. And generally phase transitions have an extremely sudden drop that goes to zero, because it's like when ice turns into water, it's a very sharp transition. It's not like ice turns into water roughly in the range of minus 20 to 20. It exactly at zero is the phase transition point. And phase transitions tend to have this very sharp behavior. And the only sharp behavior that you see here is around here at about 230 Kelvin, but this clearly looks like some kind of experimental artifact. So going back to Das Sama's tweets here, he's very scathing of these results that are coming out from Southeast University. In inverted commas, he says, physics being presented in these unrefereed preprints is a travesty. The original paper has no obvious superconducting transition, and the T less than TC resistivity is 100 times that of copper, which you also notice. Southeast also has no transition, just instrumental artifacts. That's this sort of weird drop that he's seeing at 200 and odd Kelvin. What is the goal here? No one can fool nature. Very scathing of basically both of these reports, right? Now, onto the Meissner effect. This effect of the superconductor kind of floating is one of the classic signals of superconductivity. It's the effect that superconductors can expel all magnetic fields from within them, and so this is why you have this levitation kind of effect, right? There's been also another follow-up video just this morning posted on the New York Times, and they have basically a similar type of video. Again, it's sort of floating, but not entirely floating, with one edge on the side. In terms of replication, maybe the closest to any kind of replication has come from another Chinese group from the Hangzhou University of Science and Technology, and they posted their video on Bilibili, and they showed minute fragments of this stuff, again showing this semi-levitation kind of effect, right? But the thing with this kind of levitation effect is that, and this is the criticism that a lot of people are pointing out, is that basically this effect is diamagnetism, and diamagnetism basically means that it's a material that follows the magnetic field in the opposite way, right? A lot of materials that we're familiar with, like iron, are usually paramagnets, right? So your fridge magnet that you stick on your fridge, if you put it on there, the reason why it sticks is because the fridge door is made of some material including iron, and iron is a ferromagnet, and basically it will point its magnetic field in the same direction as the applied magnetic field, right? So if there's a north pole here on the magnet, then the paramagnet will follow that magnetic field. It will have a south pole close to it, and hence it will attract. And so this is why fridge magnets stick to the door of your fridge, right? Now, diamagnets are the opposite, so the magnetic fields that's induced are in the opposite direction, right? So the north pole induces another north pole near it, and so it repels. And so this is why diamagnetic materials can repel. Now, there's this famous experiment by Andre Geim, Ig Nobel Prize winner and Nobel Prize winner. He got the Ig Nobel Prize for levitating a frog in a strong magnetic field. And you can do this because basically frogs are full of water, and so if you have a strong enough magnet, you can levitate a frog. But there's other materials like this which have quite a strong diamagnetism. For example, this pyrolytic graphite is a material with particularly strong diamagnetism, and so if you put such a material on the near a magnet, it floats, right? This is not a superconductor, this is just a regular diamagnetic material. Yes, it's a relatively strong material, it's a strong kind of diamagnet, however, it absolutely floats, right? Superconductor, of course, also floats, has a much stronger effect than this, but the fact that it floats is not 100% signal that it's a superconductor. And so this is why people have been saying that perhaps this material is just simply just a regular diamagnet. Right? Another thing that people have been going on about is theoretical verifications of basically superconductivity in these materials. One of the first papers that came out came from Sinead Griffin from Lawrence Berkeley National Laboratory, and basically in this particular work what they showed is that there's a kind of a flat band in these types of materials. Now, possibly because she tweeted this along with a mic drop gif of Barack Obama, people thought that this is absolute smoking gun evidence that this really shows that LK-99 is a room temperature superconductor, right? And there's lots of tweets about how from this result, quote, insanely bullish for humanity. But in fact, these types of results really only show partial information about how it might be plausible that superconductivity might exist in these materials. And the main result, it really is these calculations where they calculate the band structure, and basically what is found in this paper are like two bands which are very close to the Fermi levels, separated from the other bands by 130 milli-electron volts. And so why flat bands are important is because basically, if you've got very energetic electrons, which basically means that the bands are not flat, then it's harder to combine them into this Cooper pair so that this kind of condensation effect can happen, right? In a flat band case, if the electrons don't have so much energy, just a little bit of attractive force can bind them together, and then you can form this pair, and then you can form this superconductor. And so this is why flat bands are very interesting in terms of superconductive materials, because this is one way that you can form these pairs so that you can get your superconductor in the first place. But just showing flat bands isn't really the end of the story. That it just makes it plausible that you might get superconductivity. You really can't take these as just like some kind of smoking gun mic drop proof that LK-99 is going to be a superconductor. Further calculations would need to be done in order to basically prove this. Okay, so firstly, what do you guys think?
So if they're fake, why are everybody giving it that so much attention then? That's what I don't really... Because even my first reaction when Valentin posted that thing was like, okay, there goes another one of those claims. That's what I just said. And that was it. I didn't really follow it so much. I wasn't really...
I don't know why. Yeah, I think it just because it must be a combination of people just it's interesting. It's a bold claim. Maybe a lot of people want it to be true because it would be a remarkable breakthrough. Absolutely. Yeah, if it's true, people say that it's a Nobel Prize, stuff like that. But it really probably will be, right? Like it's that amazing. It's that much of a bold claim. Yes, but the boldness is breathtaking.
Besides that one paper, has any other person said something else?
Yeah, I think there's been about 8 papers or so, but just going through them, you can go on Wikipedia and then there's like a running table of new papers that are coming out on related topics, and I believe they're all actually this type of paper, this density functional paper, and they all have quite similar results actually. So they all find this flat bands, and so I think, I'm not sure if there's much variety actually in the theory. There's a little bit more variety in the experiments actually.
Experiment-wise, nobody has ever, besides the Chinese, who's tried and failed.
Yeah, again, there's, I don't know, maybe 10 experimental groups which are trying. You can again look on Wikipedia because it'll be just different tomorrow. There'll be like another 5 tomorrow. So yeah. But in terms of the main ones as of today, I think the ones with actual results that you can actually have a look at, I think it's like the maybe 3 Chinese groups, there's an Indian group, but the other ones, they say they have some results, but it's hard to find actual information. Yeah.
This LK-99 has been around since, right? I thought maybe the properties of this material should have been well understood very well before now to say whether this can happen or not.
I think what they changed, they adopted with copper or something, so I think they were working with like a variation of this material.
The properties should have been well known, or such that even if they tweaked it, you should be able to immediately say yes or no. Yeah, yes. That's what I'm trying to get at, not necessarily, but it looks like it's not.
Yeah, I agree with you. It's just a weird thing about it, because it's clear that they're aiming for superconductivity, right?
Yeah.
Because they've been playing with this material for 20 years, and I think this has been their aim for the whole time, right? And,
yeah.
This is their patent from 3 years ago. It's in the title. Like you can see, that's what they're aiming for. So why these very scratchy results, and why is it so unclear? Like they had 20 years to look at this. So I don't understand that story at all. Yeah.
I don't take Wally, because like I said, when I first saw the post, I was like, here goes another one of those fairy tales.
Yeah.
But if I sitting here and thinking, if LK-99 has been around for some time, its properties should have been well known, such that even if you tweak it a little, people should immediately tell you, okay, this is what I should expect. But it's not like that. I don't know.
Yeah, and also I think it depends upon the sample as well, right? Like so. I think different samples show different properties, and so it's, I don't know, pretty unpredictable stuff.
Maybe theories to the rescue for this one, actually.
Theory?
Huh?
You think theory to the rescue?
Yeah, I think theories in this field to the rescue.
You can only do experiment, I think.
No, I agree with you. The experiments have the final say on this, right? But at least the theory should be able to lead the way to make some interpretation about what is going on. Otherwise, everybody will be still scratching their head, because it all boils down to whether are they going to replicate what these people did, or, I mean, for experiments, either to replicate what these people did, or to come out boldly and say, okay, this material can never be this, or can never have this effect.
We can always wait for like very advanced molecular simulations, but
like experimentally they find not agreement with you.
Okay, so I think I would say that the problem with doing this kind of thing is these are strongly correlated materials, right? And there's the Qcentre superconductivity, which I think people had a lot of trouble in creating models and understanding that. You have to solve these very large spin models, which are notoriously difficult to solve, right? And it's not just like a band structure problem. Band structure is the first step. And then now you've got this strongly correlated material that you need to solve, which is like numerically like very hard. And then you have to prove it. So I think it's just, you see it in experiment, we don't, I think. Yeah. In theory can provide a few sort of indications, but I don't know, it might be hard.
So debunking this might take some time really then.
But this stuff is really easy to make, so as long as experimentally.
Okay.
People already made it, right? In a few days.
Okay.
Now they just got to kind of make it better or cleaner, and then basically everybody in the world makes it. Even people in their garages, right? They measure it, and nobody finds it, and that's it. It's the end of the story, I think. Like,
So from the statistical mechanics perspective, they claim that in this particular material, the electrons are able to pair at room temperature, naturally.
yes.
Okay.
Yes.
That's a bold claim.
Yeah, I think I didn't go into so much the mechanism, but in the second paper they claim some mechanisms of why this might happen. And basically what they say is that there's some kind of, by replacing the lead atoms with the copper atoms, there's some like kind of natural pressure that builds up in the material, which makes, instead of applying external pressure, you have some internal pressure, which kind of results in the same kind of effect. But having said that, I've also seen, again, I think the Dasama Twitter thread saying that a lot of this basically explanation is absolute nonsense. Nobody can really understand basically this mechanism as they explain it. Yeah.
But ultimately they are getting a lot of citations, positive or negative both.
Yeah.
Don't just say like it is like flow or that is not supported by the results.
Mm-hmm. So it's a good way to get citations.
Both ways. Yeah. If you are in news, then it is a way.
To conclude a little bit, I think that even though I've presented this pretty skeptically, ultimately there's still a chance that people can still find superconductors in some weird material, and it doesn't matter where you're from. It doesn't matter, you don't have to be from a great big university. I mean, there's no reason why it doesn't exist, and this is why I think people are, looking at this seriously, but with an eye of skepticism. This is just how science works. Hope you enjoyed that, and we'll see you for the next one.